Hi, welcome to our second Passion Behind Design presentation. For those of you that don't know what Walter P. Moore does, we are an engineering practice that was established over 90 years ago. We are headquartered in Houston, Texas, and have over 650 employees across 21 US locations and 5 international locations. Today we have Raphael Sabelli presenting the Air Traffic Control Tower at the San Francisco International Airport. He will share with you why he became an engineer, along with some interesting facts about seismic design. If you have any questions during the presentation, please type them into the chat and we will answer them during the breaks. And with that, I'll hand it over to Raphael.
Thank you, Annie. Hello, everybody. So I'm here today to talk about a lighthouse and a tower, San Francisco's torch for travelers. This is one of my favorite projects in my career as a structural engineer. So I'll start with a little bit about myself. When I was in high school, I really liked math, and I also liked physics when I went to college. But I also liked sculpture. So I had those two, we'll say, different aspects of my personality, and I thought they'd come together well in architecture, but specifically the type of architecture that celebrates structure and the physical feat of holding things up. And that, of course, is very important in California, where we not only have to hold things up, but we have to hold things straight during earthquakes. So my career as a structural engineer has permitted me to do a lot of different things. I write seismic design codes for steel structures. I've helped write a textbook for design of steel structures and seismic design. Currently teaching a class in design of steel structures at UC Berkeley, and I'm always very excited to talk about seismic design. For Walter P. Moore, I'm managing director of San Francisco. We have a great team of devoted and very talented engineers working here in the West Coast. So this was an award-winning project. It's my favorite little photograph of the project. We've done huge projects. The $5 billion SoFi Stadium project recently completed. Took several years of many people's careers, and it's a fantastic production. And before that, the San Francisco International Airport Air Traffic Control Tower, which is a beacon in the middle of the airport. So that's my little self-introduction, and we'll see if there are any questions that have popped up in the chat.
Not so far, so we can continue on.
All right, let's do it.
Okay.
So this was an award-winning project, and we have a little video here on that.
5527, runway 8 kilo, you're clear for takeoff.
A gleaming beacon of structural achievement, the new San Francisco International Airport Traffic Control Tower, accented by its soaring flared design and glistening metal paneling, is a dazzling addition to the Bay Area horizon. But this triumph of engineering ingenuity is more than just a pretty face. Located near the San Andreas Fault, the tower contains groundbreaking seismic safeguards designed to withstand a 7.5 magnitude earthquake, a critical component since its 1960s-era predecessor was knocked out during the 1989 Loma Prieta earthquake.
The engineering solution, the ability for this tower to remain functional even after a major earthquake. From an operational standpoint, that's a very important attribute for our airport. If you can't run a tower, you can't run an airport. And to know that this has been designed to keep going even under the worst of conditions, that's important for us.
The 231-foot-tall tower features a revolutionary cast-in-place, reinforced concrete core cylinder with vertical post-tensioning, possessing an incredible self-righting capability, and making the sleek structure amazingly resistant to toppling. When major seismic forces cause the core to bend, the post-tensioning strands respond with an extreme clamping force to snap the tower back to its initial position.
We built this little jerry-rigged thing out of stuff I found at the hardware store, and this shows the self-centering capability
of our tower on top of the building. We've got a rigid building at the base, and then we've got a vertically post-tension tower that really just articulates at the top of our base building and comes back, and that's the system.
The tower also features an innovative system to limit structural sway caused by high winds, common in the region, while the strategically offset controller cab provides clear, unobstructed views of all runways.
Resilience-based design is a hot topic in our industry right now. We want to make sure that our cities and our communities are going to be resilient after major disasters, and I think that this tower is a great example of that.
It's an amazing interweaving of reinforcement and ductwork in that foundation that is just unparalleled in my experience in terms of complexity.
It harkens to bygone days when there were lighthouses in harbors that welcomed the ships into the harbor. The airport is like a modern-day harbor and a modern-day port. The tower is like a beacon that welcomes the passengers from all over the world to San Francisco.
In safely coordinating takeoffs and landings of more than 1,000 aircraft daily in one of the world's most volatile seismic regions, the new San Francisco International Airport Traffic Control Tower achieves a new pinnacle in structural design and engineering excellence.
Still no more questions, so we can continue on.
So in that video, we talked a little bit about the seismicity in California. This is a diagram of the major faults in California with their slip rates. And the two tectonic plates, the Pacific plate to the left, the North American plate to the right, they're moving past each other. And these faults accumulate energy as the two plates try to move past each other. It's sort of locked in until something gives and a large amount of energy is released. And so we've got a lot of that energy here in the Bay Area, this little quadrant here. And you can see that there are major faults running through, some of them capable of earthquakes of a magnitude 8 or so. And so with that level of seismicity, keeping an airport operational takes a lot of engineering work. Here's the San Andreas Fault, runs through the San Francisco Peninsula, and that's the location of the air traffic control tower. So 2.5 miles apart. We certainly could see very large ground motions in the airport and specifically for the tower. Complicating matters is the fact that most of the airport is on what we call fill in the bay. So it used to be just the mud under the water, and a lot of dirt and rubble was poured in. That's where all the terminals are, and that's where the air traffic control tower sits. So that very soft ground can move quite a lot in an earthquake, and it's one of the reasons that we had to take our foundations, our building piles, which are like concrete columns, all the way down to bedrock, about 140 feet down from the surface. Air traffic control towers are tall and slender, and so when they're subject to earthquake motions, they can move a lot. In the 2001 earthquake, Nisqually earthquake in Seattle, that air traffic control tower performed very well structurally, but the degree of movement caused a lot of non-structural damage and took that tower out of commission for a few days. In 1989, there was the Loma Prieta earthquake in the San Francisco Bay Area with its epicenter near Santa Cruz, and that caused failure of the window system of the existing air traffic control tower. So for these reasons and update in technology, it was decided to replace that old air traffic control tower with a new one. And here's a photograph of the old air traffic control tower, and I'll just ask you to pay attention to what we call the mullions, which is part of the structure that holds the glass. These serve an important structural function, but they also create essentially blind spots for the air traffic control tower, for the air traffic controllers that they have to work around. And we'll see how we handle that a little differently in our tower. So here's an aerial view of the airport and highlighting the old tower and our new tower, which is significantly taller. And here the two are side by side.
Okay, we do have some questions. So the first one is, what was one of the main goals for this project?
So for the airport, the airport had a couple of important goals, and they were very, very clear about them, which is great. It was great for a client to be. They wanted the tower to remain operational in a large earthquake, such as the Loma Prieta earthquake that happened in 1989, or even larger earthquake. And that means preserving the function of all the equipment in the tower, of course, preserving the glass, preserving the accessibility. And the reason for that is that after a major earthquake, it's very important to be able to bring in relief, people, supplies, etc., not to shut down one of the major airports in the area. And then for what we call in the engineering profession, the maximum considered earthquake, which is a very, very large event, they wanted to protect the safety of the air traffic controllers. So that would be an earthquake that levels a lot of buildings in the area, and perhaps takes the airport out of commission for other reasons, such as the runways. But do want to make sure that there's no collapse or anything that would threaten the safety of the air traffic controllers.
Okay, thank you. So you'll love this question. The next one is, can you explain seismic codes and how does one create a code?
So seismic codes are put together by a group of people who we'll call ourselves experts. There are different sources of expertise. There's experience in design and construction. There's experience in past earthquakes, and there's experience with research and analysis. And all of these things come together. So we have knowledge that we've gained from visiting sites of past earthquakes and seeing how buildings have performed. And we have knowledge that's gained from analysis, computer analysis of buildings. And we have knowledge that's been gained from testing in structural labs to see how things behave. And each of these is limited, of course. The earthquakes come every so often, and they don't affect every new technology. So there's some uncertainty about how the new technologies will actually behave. The computer analyses, they're only as good as they're calibrated to real behavior of real systems. And so that's an ongoing consideration. And then testing in the lab, our labs can only test things that are so big or so complicated. Usually it's not complete buildings. Usually it's smaller scale representations of structural elements or subassemblies. But when we put it all together and confer over years, we are able to create a system of design requirements and recommendations that lead to much higher reliability in a seismic event. And that's been proven out with how new construction has fared compared to older construction in earthquakes around the world.
Okay, another great question. How do you think climate change is influencing the role of engineering?
That's a great question. So there are a couple of different aspects to that. One is, where our buildings sit, how the winds, the tides, the other things that affect our buildings. All of these things are potentially subject to climate change. Earthquakes, not so much, but a lot of other environmental considerations can be influenced by climate change. But another very important aspect is the energy it takes to put a building together, the energy it takes to make cement for concrete, to move building materials, and the energy that buildings use in heating and air conditioning especially. So those last two aspects are really the focus of our sustainable design in the last 10 or 15 years, improving our performance in terms of how much energy it takes to put a building together, and then improving our performance in how much energy it takes to keep a building running. For seismic design, it's important to note that if a building has to be torn down after a seismic event, that's a lot of wasted energy, not just tearing it down, but the energy involved in replacing it. And so surviving an earthquake and keeping the building operational also has a sustainability dimension to it.
Okay, we just had one more question come in. What was the most difficult part in building a structure on top of a landfill?
So one of the most difficult parts of building structure on landfill was determining the seismic accelerations at the site. And our geotechnical engineers working with us on the team did a fantastic job in modeling the soil underneath, both before we had the foundation system, and then with these some 160 piles being driven through it, modeling how those seismic waves propagate through that up from the bedrock to the surface. And then once we had those surface motions, analyzing that effect on our building was a structural problem, and that took a lot of engineering work as well.
Okay, these are great questions, everybody. Thank you. Keep them coming. Another one, what made you interested in this topic?
So I was actually in school during the Loma Prieta earthquake. I was studying architecture, and it really affected everybody. I was at Berkeley. It affected people differently. I grew up in the Midwest, and the ground more or less stayed where it always was. And the earthquake was essentially a great leveler. It changed dynamics. It changed people's daily schedule for a month. The Bay Bridge was out of commission, and the train system was shut down for a few days. And really, it really was an important event, and it got me interested in seismic design.
Okay, so no more questions right now, so we can continue on the presentation, and we'll circle back. So keep asking questions, everyone. Thank you.
Yeah, thank you. All right, so here's our little toy, and the toy is really it's modeled on the behavior of a children's toy, this sort of push button, self-centering thing. But if you've ever played with that toy, you understand what happens. It's the tension in that vertical string that pulls things into alignment. The tension works in combination with compression on those little wooden pegs and clamps together any cracks. And so when a building, a concrete tower like this, is hit with a lateral force, horizontal shaking due to the earthquake, it can bend, and when concrete bends, it forms these tiny cracks, which are not in and of themselves a problem. These long vertical lines, these are the cables that are in tension, and when the building is displaced like this, the cable on the right side here, where there are no cracks, it doesn't need to elongate. But the cable on the left-hand side, where there are the cracks, it has to elongate. And so it has this clamping force that will close these cracks back up. So the cracks can happen, but they are instantly clamped back. Now, to keep that tension force, we need to tie the cable off at the top, and we need to anchor it into the foundation here. And it needs to go through a lot of concrete reinforcement there to be fully anchored. So that's the structural scheme. Of course, we needed to prove it out. We couldn't test it in a lab, so we analyzed, and we always like more analysis. So here's our analytical model, And we had, this is obviously greatly amplified compared to the real motions, but we had a number of different ground motions recorded from different earthquakes and scaled to represent what would happen at the site. This is the movie San Andreas, which is kind of fun because in the movie San Andreas, just about every building in the Bay Area is knocked down, except for our air traffic control tower. It's nice to see it still standing there. We talked about those mullions. One of the things the client wanted, we had two clients. We had the airport and we had the FAA. And the FAA has, of course, a lot of guidelines for their air traffic control towers. For the modern ones, they want 210 degrees column free. So this is like a plan view, the footprint of the control tower cab. And so we were able to provide 235 degrees without columns. So these are our columns. We've got a major column right in the center of that space, and then 3 other columns around, and then no columns for 235 degrees. And that means the view is incredible up there. This is the structure with that big central mast column, and then the other columns behind holding it up. And if you stand in there with your back to that mast column, as I did during construction, you can see the whole San Francisco Bay, that 235 degrees, little panoramic view. This thing is the tower crane that was used to build the building, later taken down. So that's an incredible view. And then the architects did a fantastic job in detailing the glass. And you can see the glass is just faceted with a little bead of silicon in between. We don't have any of those mullions. And so the air traffic control towers have the best view from our new air traffic control tower. We're very proud of that.
Okay, we have one more question that came in. If the tower does buckle, will there have to be construction or repair done? How does it pop back up?
So in a moderate to severe earthquake, the tower is self-centering. That vertical post-tensioning pulls it back to plumb, and there is no repair needed for that. Now, where it articulates, there's a lot of attention paid to, say, the cladding, the stairs, everything else that needs to move across that joint. So the structure, in some sense, is the easy part. Everything else that you'd think is continuous, like the waterproofing, all of that has to be carefully detailed to allow for that movement and not to damage itself in a major event.
Hi, my name is Laura Whitehurst. I live in New Zealand now, but I used to work in San Francisco and worked for Walter P. Moore. And I was lucky enough to get to work on the San Francisco International Airport Air Traffic Control Tower during both the design and the construction phases. I really loved working on such an iconic and innovative project, and during design it was really exciting to be pushing the bounds of seismic design, especially because we were explicitly trying to design a building that would be resilient after an earthquake. Making sure that the tower could be operational after a big event means that the whole region can get back to normal much quicker. And during construction, I really loved working with the team of contractors and other designers like the architects to solve problems that cropped up during construction. And it was so thrilling to watch our design that we had been putting on paper come to life in real time. And it was really cool to have it be so visible too. You could see it from the highway, you could see it from the trains. And so it was really neat to be able to show it off to the public and to show it off to my friends and family, and to be able to explain all the various structural features like the self-centering aspect of the tower. I still do that now, but it's a lot harder now that the cool facade has been put on.
All right. So here's our team. The night of the first concrete pour, it was 14 hours of concrete poured for that foundation. You can't have cold joints in that foundation, so it was continuous truck after truck, which we watched here from the tower crane. And over a year later, we had what's called the topping out ceremony, which is something special in construction. When the last piece of steel is placed, a lot of people, the engineers, the contractors, everybody on site, they will sign their name to pieces of steel or a piece of steel that's hoisted and placed, and that's the last piece of steel in the roof of the project. And so there's our team. We have all our names written under on that last piece of steel. Here's our construction. So the contractor had a camera at the airport side, what we call the land side, and another one at the air side. So the left is the land side, you can see people being dropped off. And on the right, you have the air side, you can see the gates still in operation. And the tower goes up, and then the steel frame is put on top of it. And then the skin, first the weatherproofing, and the skin is placed around it. And that's how you build an air traffic control tower. All right, so that's the end of the presentation.
All right, we don't have any more questions right now, but we'll give it a couple seconds and have people type in any last questions. I have one, actually. How long did it take from start of construction to end of construction to build the control tower?
It took approximately 2 years. The difficulty in answering that question is the end of construction really petered off because there was so much work involved in the electronics, the outfitting of this control tower with electronics and commissioning those systems. And so for several months, we were actually reviewing holes being drilled a little bit through the concrete to pass different electrical systems through. So that part dragged on a little bit, but most of the construction was over the course of that first year.
Okay. Okay, a couple more questions came in. Why did it take 14 hours to lay foundation concrete?
It's just the pure volume. So underneath this tower, which is 220 feet tall, the foundation is 7 feet thick, and then it tapers to 3 feet thick under the base building, and so it just takes a lot of trucks of concrete to place that much. Also complicating it is this is in an airport, and so access for concrete trucks is a little bit limited. The contractor chose to do it overnight, which I think was, absolutely the right choice. And the airport was able to open up a sort of back road through the airfield when the gates weren't in use, and so the trucks mainly came that way in the back way. But it was nonstop for 14 hours over. I can't remember the number of trucks, but it was an amazing event, and when it was done, it was 7 foot thick, reinforced top and bottom, and we're ready to build the tower.
Okay. What was the most exciting part of this project?
One of the real exciting parts was, one of my favorite parts of the project was it's right in the San Francisco airport. And so I did a fair amount of traveling during the design and construction. We had a little remote office set up in the airport, and so I got to see every phase of construction. Either a visit to the site, or if I was just flying somewhere like to Los Angeles, I would stop by on the way, and so I got to see it really from start to finish, the way that very few projects had been able to follow that closely. And because it's so close by, I was able to take my family to see it. On one day, I took I took my son Nico on his birthday to just to show what I do for work. And when we arrived there, the superintendent waved at us. I waved back, but no, he waved at us to come up. And so we had Nico outfitted with a construction vest and a hard hat, and we rode the construction elevator up to the top and got to see a great view. So that was a really exciting part for me.
Nice. Okay, next question. Would you work on an air traffic control tower again?
I would absolutely work on an air traffic control tower again. For one thing, you learn a lot, and when you learn a lot, you want to apply it again. So that's something. Also, it's just it's such a beautiful sculptural form. It's I know a lot of air traffic control towers can be fairly rough, but I think they're all beautiful.
Okay, next question. How do pandemics affect projects like these, and how do you account for it?
So there are a couple of different aspects to how pandemic has affected, my profession and my industry. So my profession is structural engineer, and my industry construction. So I think we had a couple of months early on where nobody was really sure about how contagious things were, and a lot of job sites were in San Francisco were shut down. And then with some more knowledge and a little bit more care, by and large, contractors set up reasonable ways of working, at least in outdoors, with very little risk of contagion. That's not to say that it was always effective and that everyone did as good a job as everybody else, but construction was able to go forward on a number of projects before everyone was vaccinated. For the profession of structural engineering, we in my company, as Annie described earlier on, we've got a lot of offices. This particular project, for example, it was all pre-pandemic, but it was delivered, largely out of three different offices: Austin, San Francisco, and Los Angeles. We had teams working on different aspects of the design, and so for many years we've been working in teams with video meetings and the like, and so we were reasonably well set up to do that when the pandemic started, and so that aspect hasn't been too bad. I think it is an issue for our younger engineers and our new hires. It's very good to be able to meet people face to face and to draw things on the whiteboard or on pieces of paper next to each other. And we do make do with our net meetings, but I think there's something to be said for meeting face to face, and we'll probably have as much of that as we can as we come out of this pandemic.
Okay, what are the biggest challenges of working at an airport?
Logistics are a big problem. So logistics means how you get things and people where they need to be. So everyone, every airport has a very important security boundary between the land side and the air side, and that boundary has to be maintained. And usually the construction wants to be all on the land side, with the security maintained at the far side of the construction site, usually. But that's not always the case. So making sure that boundary is maintained, and then making sure that you can bring in 40-foot long beams and concrete trucks and the like at an airport that wants to look clean and pristine and welcoming, and doesn't want to have a lot of mud and construction dust everywhere. So to give you an example, all of the foundation work, every truck that left the site was cleaned before it went out through the airport. And that's a lot of effort. And in considering what foundation type we would use, we had to consider how the noise might affect the airport operations. And we had to consider also, whether we were removing any dirt, and therefore we'd have to go through all of the complications of moving things through the airport. And of course, I should mention the construction crane, is very tall. Fortunately, it's not in the airfield, but it is still very tall, and that had to be considered for the FAA to make sure that it wasn't going to interfere either with operations or with visibility.
Okay, next question. What does the old tower do now?
So the old tower, my understanding is that they've already done some of the work, that the old tower is being dismantled and removed partly as part of a renovation project for that terminal, but also part of it was obscuring just a little bit of the view from the new tower. But it's a great location. If they could keep it, I would say, the airport director would want to have their office up there, because it's a great location.
Okay, next question. If the pandemic hit before you were able to finish the tower, how would things be different in regards to finishing the project?
I would think the pandemic would cause delays. One of the complicated things about an air traffic control tower, so we already talked about the complications of working in an airport. One of the complications of air traffic control tower is that the technology is really intensive. All of the electronics and radio and antenna systems. It's very dense with that, and it's a pretty small footprint up at the top of the tower. So you're bringing a lot of people close together, and it was already complicated just getting those people up and down. Before the elevator was commissioned, just working on a construction elevator, which is a little bit rough, getting people up and down. That was already complicated, and if you factored into that the need to keep people apart to minimize the risk of spreading COVID, that would have slowed down. That would have limited the number of people who could work, and caused that outfitting to take much longer.
Okay, that was the last question. So thank you all for joining us, and we hope to see you on our next session. Thank you.
Thank you.